Good afternoon, respected dignitaries, esteemed guests, faculty members, and dear participants. I welcome you all to the session 3 of the National Conference. I now invite Hyacinta Charles of 3rd BSc Food Science and Nutrition to introduce the chief guest.
It is my great privilege and honor to introduce our esteemed speaker for today's technical session, Dr. N.G.P, who will be presenting on the highly relevant and futuristic topic, AI applications in biological sciences. Dr. Sukumar currently serves as an adjunct professor at the Amrita Vishwa Vidyapeetham School of AI, Coimbatore. He is the founding head of the Department of Chemistry and the founding director of the Center for Informatics at Shiv Nadar University, from where he retired as professor. He completed his MSc in Chemistry with first-class distinction from Indian Institute of Technology, Kanpur, and earned his Ph.D. from the State University of New York at Stony Brook. His remarkable academic journey includes prestigious postdoctoral and research appointments at globally renowned institutions such as the University of Southern California, University of New Orleans, Marquette University, and Rensselaer Polytechnic Institute. Dr. Sukumar is a distinguished recipient of the Alexander I Humboldt Fellowship and has also served as a visiting scientist at the Wadsworth Institute and at the Institute of Mathematical Sciences. His research expertise spans quantum chemistry, density functional theory, cheminformatics, bioinformatics, protein ligand modeling, molecular descriptors, and machine learning-based materials and drug design. He has made significant contributions to AI-driven molecular discovery, chemical space exploration, and computational drug discovery. Dr. Sukumar is also an accomplished author and editor of several scholarly works, including A Matter of Density, published by Wiley, Computational Drug Discovery, a Primer 2023, and his recent Springer publications on molecular networks and artificial intelligence in materials informatics. With decades of interdisciplinary experience integrating chemistry, biology, and artificial intelligence, Dr. Sukumar truly exemplifies the convergence of computational science and life sciences. We are deeply honored to have such a distinguished academician and researcher among us today. Ladies and gentlemen, please join me in warmly welcoming Dr. N. Sukumar for his technical session on AI applications in biological sciences. Thank you.
Thank you, Hyacinta. I request Dr. Shivakumar Sir, HOD, Department of Medical Physics, to honor the chief guest with a shawl. I now request Dr. Kokila. Thank you, sir and ma'am. I now request Professor N. Sukumar sir to take over the session.
Thank you for the invitation and for the opportunity to speak here at this conference. So what I'll be talking to you what I'll be talking to you now would be on a specific aspect of application of AI in chemistry, in chemical and biological sciences, specifically for the design of drug molecules and materials for specific applications. So, what is the motivation for using AI here? The motivation is the long timelines for drug discovery. As you can see here, the timeline from the identification of a molecular hit to the development of a viable drug has typically taken 10 to 15 years, and it costs about $1 to $2 billion. So that's a significant investment and a significant time. And if we can cut short that process, then that is one of the motivations for drug discovery, for using AI in drug discovery. So we want to find a correlation between the atomic level structure and the molecular properties, so that with any number of molecules, including molecules which have not yet been synthesized, we call them virtual molecules, can be screened in silico to select structures with desired properties. So we see that the rate of failure of molecules is very high in the initial stages. So we start with thousands or tens of thousands of compounds, and then finally we'll be lucky if after spending 8 or 10 years, if 1 or 2 molecules make it into the final stages. Many of them fail during the late stages of the drug discovery pipeline, which means that a lot of money has already been invested and a lot of time has been invested. So our objective here is to actually fail sooner. If you're going to fail sooner, fail cheap, right? Don't spend 5 years in college and then fail. If you feel you're not cut out for this, fail in your first year and go to find something else to do, right? Same here. So, and even for materials design, you see that if you look at many of the materials which have been developed over the last 60 years or so, it has taken 20 years or more for a newly developed material to make it from the lab into the market. Okay. So there's the various applications, areas of materials informatics. Okay. So as I said, the motivation is to find this correlation so that we can screen molecules in silico. So the virtual screening can weed out the compounds with adverse side effects or toxic side effects, identifying the losers early on in the game. Okay? So you don't want to work 10-15 years on something and then have it fail due to toxicity or something like that. Okay? So therefore the most promising compounds can then be chosen for laboratory synthesis and preclinical testing, thereby conserving resources, leading to cheaper medications and materials, and accelerating the process of drug discovery from this 10-15 years to something within a short timeline. And we saw this actually during the COVID pandemic, when within a space of a few months, 1 year or so, several potential vaccine candidates were actually developed, tested, and made it rolled out into actual clinical practice. Well, the number of possible molecules, when you say that screen virtual molecules, okay, how many virtual molecules are there? That's huge. It's worse than searching for a needle in a haystack. The chemical space of molecules obeying the rules of valence and which are likely to be drug candidates, which are possible drug candidates, is about 10 to the power 60. That is far, far more than the total number of atoms in the entire universe. Okay? So just systematic search or random search is not going to get us anywhere. Okay? And searching in the right region of chemical space is critical to the success of a drug discovery project. You might have heard the joke of the drunk person who was searching under a lamppost, and when he was asked what happened, he said, "I'm searching for my keys." He said, did you drop them here? I said, no, I dropped them way over there. And why are you searching here? That's because here's the light. Okay, there's no light. Okay, so of course he's not going to find it. Right? So searching in the right region of chemical space in this vast chemical space is critical for a drug discovery project. So as I said, we want to find the relationship between the structure and the property, and that is generally done by constructing a molecular representation. Now, software engineers call this process featureization, and then we use machine learning, AI, to make a correlation between this representation and the property. This is generally a mathematical representation or a numerical representation. Now, recently, we also have the possibility, which was earlier considered not possible, to go directly from to predict that a structure given a desired property. So if you want a particular property, what is the molecular structure that will give you that property? This was earlier considered an impossible task, but now with generative chemistry, that is becoming possible, and we'll see some of that as we go along. So, as I said, we have molecular representations. What are these? Well, molecules are normally represented as 2D formulas or 3D models. So structures that you draw on the board, that's considered a 2D, two-dimensional formula, because you're drawing it on a board or on a piece of paper. 3D model is the three-dimensional model which has actual bond lengths, bond angles and all that, which the 2D model does that. 2D model just tells you what atom is connected to what atom and what's the bond order and things like that. So 2D representations are derived purely from the molecular topology or connectivity of the atoms. 3D representations are derived from the coordinates of the atoms in three-dimensional space, so they have the actual distance information, distance and angle information. Okay. Now we can also represent molecular systems by one-dimensional strings, like for instance in a nucleotide sequence in DNA or RNA, or an amino acid sequence in a protein, can be represented by a one-dimensional string or letter codes like of this of the DNA strand shown here, for instance. Such representations are also possible for molecular systems, and this is commonly known as SMILES strings. If you're not familiar with the SMILES notation, you can see some of these, and I won't go into them in detail, but this for any structural formula, you can actually write a SMILES string. The thing about the SMILES string is that they consist of only ASCII characters, characters that you can find on your keyboard, and therefore they are machine readable. So they're not only humans can translate, it's rather somewhat obvious, but machine readable. The computer can also read this and translate it. Okay? So it doesn't matter whether it's straight chain compound, branched compound like this, you just represent these parentheses to represent the branches, or whether it's a cyclic compound, and here you represent these paired numerals to represent the closing of a cycle, aliphatic or aromatic. Even cis-trans isomers can be represented. Even optically active enantiomers can be represented through these at and at, and so forth. Okay. So we see we have string-based representations, and we also have graph-based representations. We have 3D coordinate representations and numerical descriptor representations. Now this shows you a graph representation. So for a molecule like this would be the SMILES string, and this is what is called the adjacency matrix. So here we just, the octagonal elements just represent which atom is connected to which atom. Carbon 1 is connected to carbon 2, right? Carbon 2 is connected to 1, 3 and 4, so carbon 2 is connected to 1, 3 and 4, everything else is 0. So given a string, you can, the SMILES string, you can construct an adjacency matrix. Now a variation of this is the atomic number bond order matrix, where along the diagonal instead of 0, you have the atomic number of the atom, and along the off diagonals instead of just 1 and 0, you have the bond order Okay? So that way you have the complete representation of the molecule. Okay? So, as we see, string-based and graph-based representations are actually equivalent. They contain the same information. Yeah. From this, you can compute certain molecular descriptors, which I will not go into, but there are thousands of descriptors that you can calculate from either the string-based or graph-based representation or from the 3D coordinate representation. You can calculate numerical descriptors. For instance, this is the 2D structure of this molecule. This is the 3D structure, 3D molecular model. And from this you can construct a van der Waals envelope, and you can plot a particular property, like say the electrostatic potential, on the van der Waals surface of the molecule. And then you can sample this property at various points, and that gives you a numerical representation. Okay. So, what are some of the challenges in drug discovery? First, that you have to, it's a multi-parameter optimization. Okay? So, the molecule has to be potent, right? So, you want to be able to swallow one tablet and cure your headache, not, have 1,000 tablets or eat 1 kilo of some drug in order to cure your headache, right? So it has to be potent. It has to be selective, right? If you want to cure your headache and that gives you some other problem, right? If it causes sleeplessness or if it makes your hair fall out, okay, you don't want that, so it has to be selective. Then for an oral drug, why oral drug? Most drugs are oral drugs, tablets that you can swallow, because for something, if you want an injection, you can't tell a person come 3 times a day to get this injection, right? Particularly somebody in some remote village, you can't tell them come 3 times a day to get this injection. You can do it as for an inpatient, you can't do it for an outpatient. So most of the drugs we try to find a oral drug that you can swallow. So for the oral drug, it needs to be able to be absorbed by the epithelium. Then it needs to be distributed, it has to get to the target organ, and it should not be metabolized into something else before it reaches the target organ. Then the metabolic products, once it has acted, the metabolic products should be excreted, removed from the body, and of course neither the drug nor the metabolic products or anything should be toxic. Okay. So we have to take care of all these properties in addition to potency and selectivity, so that's a multi-parameter optimization. In addition, if you're working in the drug industry, well, you have to see that what does it cost to synthesize a molecule? How many steps is the synthesis? Does the synthesis take? Does some other drug company already have a patent on this drug? If so, then they will not let you market this drug. So these are things that you have to bear in mind in addition to these. The greatest of these hurdles is the absorption, distribution, metabolism, excretion, and toxicity, which actually causes 90% of drug failures in the late stage of the drug discovery pipeline. So this is what we want to model early on, so that if we can predict this, we can throw away the failures early and just concentrate on the non-toxic and favorable candidates. Okay. So these are several layers that the drug has to pass through in order to be absorbed and get to the target organ for an oral drug. And the most significant of these is the epithelium. Back in the so what are the factors that affect the permeability of a drug through the epithelium and other layers? Well, first is the molecular weight. Right? The very high molecular weight molecule will not permeate or will be blocked. Right? Then there is the lipophilicity, and this is commonly modeled as a ratio of the octanol solubility to the water solubility. Right? If a drug is very much more soluble in water than in an organic layer, then it will stay in your stomach and it will not be absorbed by the epithelium. Likewise, if it is very highly lipophilic, then it will stay stuck in the epithelium and it will not get into your bloodstream from the epithelium, because then it will get to pass through the epithelium, get into the bloodstream, and then go into the target organ. So then, if there's a large number of hydrogen bond donors or acceptors, then it will just form hydrogen bond donors to the fatty layer, and it just stays stuck there. It will not move. So these are things which you have to bear in mind. So in 1997, Chris Lipinski at Pfizer found a simple mnemonic device, which he called the rule of 5, to predict this absorption of the molecules. There are actually only 4 rules. Others called rule of 5. That's because each of these rules has 5 or a multiple of 5 in it. So poor absorption or permeation happens when there are more than 5 hydrogen bond donors, right? 2 hydrogen bond donors will just form hydrogen bonds and stay stuck, will not move. If the molecular weight is over 500, if the log P is over 5, and if there are more than 10 hydrogen bond acceptors. Okay? So, and this was a major breakthrough in cheminformatics. Since then, all drugs are actually screened for the Lipinski's rules of 5. And if a drug violates many of them, if it violates one rule, that's still okay. But if it violates 3 rules or 4 rules, then people won't even bother with it. Of course, not all drugs need to follow Lipinski's rules of 5. There are compound classes which are exceptions to the rule of 5, which are antibiotics, fungicides, proticides, antiseptics, vitamins, cardiac pesticides, and so forth. You see here that the chemical space spanned by the antibacterials is very different from that spanned by the CNS drugs. So CNS drugs are here, which follow the Lipinski's rule of 5, rules of 5, but the antibacterials don't follow the Lipinski's rules of 5. They have higher molecular weight, lower lipophilicity, and so forth. Okay. So, let's turn to AI and machine learning now. As you might have encountered already in the talks today, different kinds of problems you can deal with. You can deal with regression problems, which is predicting the new value of a variable based on the past or inference, or calculating values for a dependent variable based on the values for independent variables. So if you know x1, x2, x3, x4, then predict y. So write y as a function of x1, x2, x3, etc. Okay, and you predict y. So that the independent variable are the x's and the y is called the dependent variable. So that's a regression. Classification, divide the data into discrete classes using a training set of previously labeled data. So you have a database of molecules which include both say toxic molecules and non-toxic molecules. And you see what is common to the toxic molecules and not common to the non-toxic molecules, so that you can make a classification model and predict now to given a new molecule which whether it will be toxic or non-toxic. Okay. Clustering is partitioning into several clusters. It's actually similar to classification, but classification requires that you have a labeled data set, the training set, whereas clustering just uses the characteristics of the data in order to do that. Okay. So, and there are, you can also classify machine learning methods into supervised, unsupervised, and reinforcement learning. There are other classifications also in between, or semi-supervised and so forth. But in unsupervised, the model is not provided with the correct results during the training, and the clustering into classes happens just on the basis of the statistical characteristics of the data. In supervised learning, you have a training set for which you know the value of the dependent variable. You know whether it's going to be toxic or non-toxic. You know whether it's going to be an anti-cancer drug or not an anti-cancer drug. And you train it on that, then use it to predict. So you build a model based on the training set, and then use it to predict new compounds. Okay? And here the model is to be able to generalize, that is, it has to be able to give the correct result when given new molecules, not just be able to predict the old molecules which are there in the training set, but to predict new molecules. Okay? And so reinforcement learning we'll talk about later, that is learning from the errors in the data. Okay, so it's always important to know what you can do wrong, okay? How you can go wrong. Okay, so these are two kinds of errors in classification. Okay, this is obviously a false positive. Okay, and telling this man you're pregnant. This is a false negative, telling the obviously pregnant lady you're not pregnant. Okay. Now, in a project, in any application, the cost of these are not equal. The cost of this kind of mistake and that kind of mistake are not equal. For instance, if somebody has cancer, or you suspect somebody has cancer, and they get screened, and then you say that you don't have cancer, but the person actually has cancer. Okay? Then what happens? The person goes home. What did I say? Have cancer? Okay. The person doesn't have cancer, and you say you have cancer. Okay? What happens? The person gets a lot of stress. They have to go in for more tests, and finally you realize that no, the person doesn't have cancer. Okay? So a lot of expense, a lot of stress, but that's all. But suppose the person who has cancer, you told them you don't have cancer, then the person doesn't do any more tests. The person goes home happy, but a few months later, cancer metastasizes, and by that time it's too late. So that is a much more serious mistake. Okay? Then this cost of these vary from problem to problem. Okay? So this is called the confusion matrix, where you have true positives, true negatives, false positives and false negatives. And as I said, not all errors cost the same, and there are various metrics you can use. Accuracy actually is the total of this plus this divided by all the number of molecules in your data. So how many you got right. Recall is the number of positives that you predicted correctly. Specificity is the number of negatives that you predicted correctly. And precision is how many of your predicted positives are actually positive. Okay? And you can define a false discovery rate and an F measure. This is and the variance which is called the balanced accuracy. These are actually more useful when you have an imbalanced data set. So for instance, if you have a data set where you have a few positives but a large number of negatives, then if you just use accuracy, then you can say I'm predicting 90% or 99% of them correctly. But if somebody who just says everything is negative, that person will actually be predicting better than you. Okay? So again, then if you just go into the lab and random pick up any molecule, the possibility of that molecule being an anti-cancer drug is going to be very low. Okay? In such cases, accuracy is not a good measure, and you need a balanced accuracy. You also plot something like this, which is a specificity versus sensitivity. This is called the ROC curve. This curve is called the receiver operating characteristics curve because it was first used in signal and antennas receivers evaluating the signal to noise ratio. And the area under this curve is a measure of the goodness of your measure. You want, if you just random, if you're predicting at random, then you will be going along the diagonal. But so if you're a good model, will have a higher area under the curve, will go like this. Okay, so as I said, you need to be able to generalize. What is generalize? You don't panic when you see new data. Okay? So if your teacher asks you in the exam the exact same problems that you were given in the homework, then anybody who has marked up the homework assignment will do well in the exam. Okay? But that doesn't always judge how well you have learned the principles. But if you actually learn the principles that were taught, then even if you get a different problem in the exam, you do well. Okay? So that's what you want. You should be able to generalize with new data, not just the data that we have already seen before. Okay. So overfitting is when you do very well on the old data, on the training set. So you are modeling the training set very well, but when you are given the new data, you fail miserably. That's called overfitting. In a regression problem, for instance, this would be actually overfitting, this would be underfitting, and this would be right. Okay? Now you should always bear in mind that this is in relation to the error bars in the data. Okay? If your error bar is this much, then all of them would actually fit the data equally well. Right? Okay? So you always should, given the data, you always should ask what is the error bars in the data. Unfortunately, this is not, it's not always reported, the error bars in the data, but that is actually very useful for modeling, because without that you can spend a lot of time trying to get every single point on the line, but you are actually modeling then the noise and not the signal in the data. Okay. So what you do is generally you train your model, and you divide your model into training set and validation set. Validation set has molecules which are known activity, but you don't show the thing. You don't use those activities. You just train on the training set, and then use it to predict the validation set and see, okay, how well am I doing on predicting the new data. Okay. So as you keep training, the error of the training set will keep going down as you add more parameters. The error of the training set will keep on going down, but the error of the validation set, that means on new molecules, will actually first go down, but then it will start going up. That's that point. That's in this region you are actually overfitting. You're adding too many parameters to the data, and you're overfitting, trying to get all of these little things. You don't want that, so you stop right here. That's called early stopping. Okay, so the general procedure for model building is you divide your data set into a training set and a test set. Training set you further divide it into a training and a validation set, and you keep going through this loop trying to get the best. You train on the training set, but you keep changing the parameters until you get the best external prediction. That means not on the training set, but on the validation set. Once you have the best validation prediction on the validation set, then you go and use it to predict the test set. The test set has been kept separate. It has been kept in a locked box. This model never gets to see what molecules were there in the test set. Okay? And if that totally unknown molecules, they were not used either in training or in tweaking the parameters. Right? Those entirely unknown molecules, that how well the model is going to be able to predict that is your actual predictivity that you should report. Okay? So as I said, this test set was never seen by the model during the training process. There's some tests you can do, like by scrambling, which I'll talk about a little. And then of course you should bear in mind that all modeling is actually telling you about correlations, it's not telling you about causation. Okay? So two things can be correlated, but they need not always be causative. Okay. So I'll talk about some methods, traditional machine learning methods, before I go to the deep learning methods, which are more popular nowadays. So one of the very good methods for machine learning is support vector machines. So here you want to separate the black points from the white or unfilled points. Okay. So you normally would draw a line, which is called a classifier. But in support vector machines, you actually draw two lines, two additional lines which are called the support vectors or the auxiliary hyperplanes. In just 2 dimensions, this is going to be a line. In 3 dimensions, it's going to be a plane, and in many dimensions, it's going to be a hyperplane. Okay, so in your the axis in this are the different descriptors that you're going to use in the model. So if there are many descriptors, you have n descriptors, you have an n-dimensional space, and in chemical space in which you are predicting it. So what you want to do is then you want to maximize the separation between the hyperplanes. That will give you the best possible separation of the data. Because this data, you can draw the line like this, or you can draw the line like this, or you can draw the line like this. All of those will predict the training data equally well. Okay? But this one, which has the maximum separation between the hyperplanes, that is the most robust model. Okay? And these points which are lying on these hyperplanes are called the support vectors. Okay? So that we attempt to maximize the margin, the separation between the hyperplanes. Okay, well, your most data sets are not neatly separable like this using a line or a plane or a hyperplane. What if your data is not linearly separable? Okay. Then you do some kind of transformation into a higher dimensional space in which the data is linearly separable. This is called the kernel trick. And this function which affects this transformation from this space to that space, that is called the kernel function. Okay. So this is called kernel-less here method. In regression, normal regression, you try to minimize the training error. Okay. So y is the actual value, and f of x is your predicted value. You try to minimize that. Okay. But if you do that, then you get this white curve, F2, which is actually overfit. Whereas F1 is probably the best fit to the data, the blue line. Okay? So overfitting is likely when you have a highly non-linear function like this, or which is called a high capacity function. Okay? And what does that give you? It gives you perfect prediction on your training data, but on new data, it will give you poor prediction. Two unknowns will give you poor prediction. That is overfitting. Or lack of generalization. So how do you take care of overfitting? In support vector machine regression, so I told you how support vector machines can be used for classification. They can also be used for regression. What we do in regression is instead of trying to maximize the margin, we try to minimize the margin. Okay? Here we are trying to maximize the margin and separate the data. In regression, you want to draw the best line through the data. Okay? So that is a regression line, and the closer the points are to the line, the better the fit is. Okay? The more the data are all scattered all over, that's a bad fit. So what you want to do is you want to draw support vectors and minimize keep as many points as you can within those two lines, within that margin, and you want to minimize the margin. Now, how do you take care of overfitting? That is done by minimizing not the training error, but by minimizing the sum of the training error and the model complexity. The C is the model complexity. So overfitting is avoided by controlling the model complexity C. Okay. And what you do is then, what about these points? You penalize the model for any points which are lying outside the margin. But you don't penalize them for lying within the margin. Lying within the margin, even if they don't lie exactly on the line, that's fine, that's acceptable. So you penalize the model for any points lying outside the margin, and here we are using a linear penalty. Okay. Another commonly used method, particularly for data visualization, is principal component analysis. So this is a method of multivariate data analysis used to reduce the dimensionality of a data set. And it's used in both supervised and unsupervised learning, classification as well as regression. Basically, if points are like this, then it's not correlated perfectly with either descriptor 1 or descriptor 2. But if you rotate your axis so that this is principal component 1, this is principal component 2, then your data is well correlated with principal component 1. Okay? So principal components are a rotation of the descriptor axis, and principal component 1 captures most of the variance in the data set. Okay? So what the principal components are linear transformations on the original data vectors that satisfy 3 important properties. The first is that the principal component 1 explains the maximum of the variance, with each subsequent component explaining the maximum of the remaining variance. And all principal components are orthogonal to each other, they are normal to each other, perpendicular to each other in the n-dimensional hyperspace. And how many principal components can you extract? That will be the smaller of the number of data points and the number of dimensions and the number of descriptors. You cannot extract more principal components than those. So it's basically represented by an equation like this, a matrix equation like this. And so from the original P by N matrix, that is P molecules with N descriptors, you will now reduce it to a P by Q matrix, P molecules times Q principal components. And then you also get a loadings matrix, which is Q by N. Okay. Give an example from our own collaborators' work. So these guys were Barry Levine in Oklahoma was trying to classify molecules into either musks or non-musks. Musks are strongly smelling compounds, and non-musks are those that don't have any particular odor. Now, this is actually a huge multi-billion-dollar industry in the fragrance industries, all the scents and ethers and colognes and all that. You need new fragrances, and you need to be able to predict which ones have a nice smell. Okay, so if you look at these macrocycles, this one is a musk, this one is a non-musk. Okay, by just looking at them, there's no way you can predict that this should be a musk and that's not a musk. Okay, but in our noses, actually, we have thousands of receptors which bind to specific molecules. Okay, and we are actually much less sensitive to smell than most animals. Animals have many more. But even we have thousands of receptors, and each of these receptors is not specific to one molecule, it is specific to a range of molecules. And each molecule again is not specific to one receptor, it can bind to several receptors. But their binding strengths differ for all of these. So we took 139 compounds like this, 103 of them were musks, 136 were non-musks, and we used 264 molecular descriptors, and we also had a set of nitroaromatics. Okay, so again here this one is a musk, this one is a non-musk. Again, it's very difficult to say why this one is a musk, this one is a non-musk. Okay. But then when we looked at the data, we find that we were able to separate the musks, that is the green compounds, from the non-musks, which is the red, although there's some overlap in here. We looking at principal component 1 versus principal component 2. When we look at principal component 2 versus principal component 3, actually, it's labeled 1 and 2, but it's actually 2 and 3. So this is principal component 1 and 2. So this is with the improved set of descriptors. This was with just 2D descriptors. This was with 3D descriptors. Now you see we get a much better separation between the musks and the non-musks. So again in principal component 1 versus 2. When we look at principal component 2 versus 3, then we see that we separate macrocyclic musks from non-macrocyclic musks, from nitro musks, from non-nitro musks. All 4 of them are nicely separated in here. Okay, so now given a new molecule, if we can using its descriptors, that will tell us where to place it on this principal component map, and that will tell us which class it belongs to. Okay. A variation of this is PLS, or partial least squares, which is basically principal components used in combination with a linear regression equation like this. Okay. Now you don't call them principal components, you call them latent variables. And Again, you will generate as many latent variables as the smaller the number of dimensions and the number of samples. And they are constructed so as to maximize not their variance, but then maximize the correlation with the dependent variable, with y. So latent variable 1 is maximally correlated with y, the dependent variable, and successive latent variables have decreasing correlation with y, and of course all of them are mutually orthogonal to each other. Now, as I said, we can calculate thousands of descriptors, but if you lump thousands of descriptors, you are likely to end up with overfitting. Okay? So we use feature selection to select the most informative features. Okay? Those features, those descriptors which don't discriminate between the different classes, or which don't. If you change that descriptor, the value of y doesn't change very much. Such descriptors we get rid of. Okay? So that's called feature selection. There are very many methods to do that. And if you get a smaller number of features, the algorithm will train faster. It's easier to interpret, improves the accuracy, and reduces overfitting, and produces valuable domain knowledge. Okay? So this is an example to show why it's important. So here was a data set, human intestinal cell line data set, ECHO2. This is actually cloned from a single individual. Single individual's intestinal cancer was removed, and those cells were cloned, and that is now a useful model for drug permeability, whether the drugs can pass through the intestine or not. Okay. So we had 27 training molecules whose permeability was experimentally tested, computed 718 descriptors, and blue shows you the training set, which is actually quite well lying on the line, but red is the training set, which is actually all over. Okay. So the red points, you can see the error bars are pretty large and they're all over. Okay. So that's it's a pretty bad model. But then if you reduce the 718 features to just the 15 most salient features, now you see that both the training and the data set are nicely falling very close to the line. So that here one axis is the actual value, the other axis is the predicted value. Okay. So simple models are better. Don't throw too many descriptors. This is actually Occam's razor, named after William Occam, which states that among competing hypotheses, the one with the fewest assumptions will be selected. But the simpler the explanation, the better. But don't multiply hypotheses unnecessarily. Interpretable models are better. But in reality, we need to be able to predict, we need to be able to balance both the predictability and the interpretability. We also need to take care of the domain of applicability of the model. This is the space in which the model is applicable. If you make a prediction on it, it's only valid within this domain of applicability. The model should only be used to make predictions within the domain. So if this is the training set molecules, the blue, okay, then this defines the domain of applicability of the model, and it can be used to make predictions on this red point, which is a new point, but it cannot be made to used to predict some molecule here or here. Okay, so just a few examples before I go to deep learning methods. So this is a data set that we are working on when I was at Rensselaer. It was actually a multi-university collaboration of 5 different universities, and we were trying to design polymer dielectrics, so polymers which are fast switching. So this was used, they wanted polymers which could discharge rapidly and recharge rapidly and store a lot of power. Okay? So when you have, when you take your electric car, you plug it in overnight and then it charges. But what if you were able to go to a petrol bunk or a charging station, plug it in there, within 2 minutes it's charged and you're ready to drive off. Okay? cell phones, we take maybe half an hour to charge it and all that. What if you could just plug it in, immediately it charges? So the car battery is storing a lot more energy than just your cell phone. So you need to be able to store a lot of energy, but you need to be able to charge it fast. For that, we need a high homo-lumo gap and a high polarizability. High polarizability to give you the charging. A high homo-lumo gap so that it doesn't break down. You charge it 3 times and then after that you have to throw away your battery. That's not good, right? And, if your phone is battery runs down after some time, battery just swells up and things like that. You have to throw away the battery. Right? So normally we see that these data are kind of complementary. If there's a high homo-lumo gap, it has a low polarizability. If it is a high polarizability, it has a low homo-lumo gap. So there's a trade-off between the band gap and the polarizability. We wanted to find molecules out here with high polarizability and high dielectric and high band gap. Okay? And we found that there are 2 components to the polarizability. One is the electronic polarizability, which is actually following that trade-off between the band gap and the polarizability. The other was the ionic polarizability, which is being caused by the molecular motion, the geometry distortion. This is just caused by the distortion of the charge cloud, the electron distribution changing. This is caused by actual molecular conformational change. This component does not follow this trade-off. So then we designed molecules with high ionic polarizability, and we screened 13,300 functional groups and picked out molecules which were predicted to have high ionic polarizability. Okay? And then built models on those. So this is the electronic polarizability of polymers. This is the training set. This is the test set. This is for the homo-lumo gap. Again, this is the training set and this is the test set. As I said, you also need to do some Y-scrambling tests. Which Y-scrambling tests, they check whether the correlation that you get is just due to chance or not. This is a chance correlation. Okay? So here we do a shuffling of the data. So you have, let's say, your descriptors and your molecules, and then in the last column you have your Y, that is the value you are trying to predict. Now you switch those Y around. The polarizability for that molecule, you take it and put it here. Polarizability for this molecule, you take it and put it there. So you basically corrupt your data. Okay? If the model is still predicting okay, with this corrupted data, that means it's just nonsense, right? It's just because the descriptors for this molecule should have nothing to do with the polarizability of that molecule. If you're still able to predict that, that means it's just an overfitting, chance correlation. So this shows you the amount of correlation, and this is the how well it's predicting, the R square. And we see that for the real model, the data is there, so it's a good R square. But for the scrambled models, these are the data out here. Okay, so the scrambled models have a very low prediction. Okay, it's predicting quite badly, which is what you expect because you have corrupted the data. Whereas for the real model, when you unscramble, without scrambling, it gives a good predictivity. If you look at the error, the real model, the scrambled models have a very high error out here, and the real model has a low error out here. Okay. So the x-axis shows you how much you have scrambled the data. Okay. This one you have not scrambled the data at all. This one you have completely scrambled the data. Similarly, for the homo-lumo gap, the real model is here, the scrambled model is here. Much better predictivity. Root mean square error. The real model has a low error. The scrambled models have a high error. So with that, let's go to the neural networks. Artificial neural networks, have layers like these with neurons, and this shows you the 2024 Nobel laureates in physics and in chemistry, both of which had to do with AI and machine learning and neural networks. So neurons are basically computing devices. Computation takes place at the level of a single neuron. Each input to this neuron has an associated weight, W, which can be modified during the training. And what you're calculating is some function f of a weighted combination of the inputs. The weights are W and inputs are this y. So you compute some weighted, some function of a weighted sum of the inputs. So each neuron computes some function of the weighted sum of its inputs, and these weights are trainable. So this is modeled after the human brain or the mammalian brain, where these weights are associated with synapses in the synapses between the neurons. Okay? And these synapses, we know, are highly plastic. That means highly adaptable learning devices. That means with training, the weights associated with these synapses increase or decrease. Okay? So the pattern recognition and information processing involves synchronous activity of groups of neurons. It's not that just one memory is stored in one location like in a computer, but the memory is actually distributed in the synapses. Okay? That's what, when you learn something, the memory is distributed among all your synapses. Okay? And it said some function. What is this function? Well, there are several kinds of functions you can use. Step function. If the sum of these inputs, weighted sum of these inputs is less than a certain threshold, then the output is 0. If it is, the neuron doesn't fire. If it is more than a certain threshold, the output is 1 or the neuron fires. So that's a very simple step function. Approximation to that is the sigmoid function. And what is commonly used in deep learning is the rectified linear neural. So how the training takes place is through the back propagation of the errors. The error between the predicted value and the actual value is actually used to change the weights of these neurons in the previous layer. Okay, so there's the error back propagation. Okay, the error is fed back to the network to adjust the weights of each synapse. So in such a way that you reduce the error. Okay, so this is the difference between a shallow network and a deep neural network, which consists of several such layers between the input layer and the output layer. Input layer normally has as many neurons as you have descriptors in your model. Output layer has as many neurons as the y values that you want to predict. If it's a single thing you're predicting, then it's only one in the output layer. But if it's a multi-objective optimization that you're trying to do, like the selectivity and the permeability and all that, then there will be that many neurons in the output layer. How many layers you have in between, these are called the hidden layers. That depends on there's no hard and fast rule to determine how many hidden layers to use. You have to try it. Too many means, too few will lead to high training and generalization error and underfitting. Too many will lead to low training error and high generalization or overfitting. There's no general rule. You have to try different things, or you have to see what other people have got success at and use something similar. So a network like this, which is used for common use for image processing, is a convolutional neural network, where you take the convolution of the input with some filter. Okay? So here you're just multiplying this times this plus this times this plus this times this to give you this 18. Okay? So that is your output layer. This is your input layer, this is the filter or convolution layer, and this is the output layer. Okay? So here is basically the input which is passed through a convolution. This is basically your filter, and also the output. You see that your convolution is coming, and then this is your output layer, the output which is coming. Okay. So how does this work? If you are trying to recognize certain digits, which numbers, this is the MNS data set. This can be drawn in several ways. You have to be able to do this character recognition. Well, each of these is something like this. Okay, and what you can ask for a particular neuron, what is this neuron doing? Okay? What is this neuron doing? Well, you can see that this neuron is actually connected to these guys. Okay? So it is recognizing this. So it is firing when you have a line out there. Okay? Another neuron might be firing when you have an edge out there. Okay? So that's connected to this thing, and you have it. So different neurons might be recognizing lines, edges, vertical lines, diagonal lines, corners, and so forth. Then in the next layer, the neurons there will be recognizing combination of those lines and edges. So what combination of those lines and edges gives you a line, and so forth. Okay, so this one recognizes this line, this one recognizes the next line, this one recognizes this line, and so forth. This one recognizes a vertical line, this one recognizes a corner, and so forth. And higher levels will detect combinations of these. Okay, so then you are then able to you train on, let's say, dogs and cats, and able to predict where is your final thing is a dog or a cat. Okay, so it scan the pixels and display the output. Now this is used in chemistry for drug discovery to classify and predict molecules. For instance, if you have toxic and non-toxic molecules, so each layer is actually learning higher and higher representations of the data. And then, so the first layer will just recognize, say, functional groups. The second layer will recognize combinations of functional groups. And the ultimate objective is to recognize which combination of functional groups will give rise to toxicity in the molecule. Okay. So, now in chemical data sets, chemical and biological data sets, you normally don't have very, very large amounts of data. You don't have billions of data points. You might have thousands of data points. So you have to train. Deep learning, however, requires training on very large amounts of data. Okay? You don't have that kind of data for, let's say, a particular disease, let's say colon cancer or something like that. You may not have that many data to train on, particularly for the rare diseases. Okay? So what do you do? Well, you train on some general data set and teach that model to learn the similarities between molecules. Okay? Once it has learned those similarities between molecules, it is called the pre-training stage. Then you feed it the cancer drugs and the anti-cancer drugs, and the anti-cancer drugs and the non-drugs, and then you train it to classify those. So that is called the fine-tuning stage. Okay? So you transfer the information from the source domain, which has a large amount of data, to the target domain where the data is fewer. So using these transfer models, you can learn the chemical information. Okay. So the different kinds of neural networks, the graph neural networks. Here the nodes represent atoms and the edges represent the connections or bonds between them. And graphs can be mapped onto properties, and they recognize the chemical environments. Okay? So, as I said, you can have the atomic number bond order matrix, something like that. So here, in the first pass, each node is an atom which has, let's say, atomic properties, let's say atomic number or polarizability or something like that. And each bond has some property like bond length or bond order or something. Okay, so that's in the first layer. Then you pass it through convolution and graph convolution layer. In the second layer, it inherits. It recognizes not only am I a nitrogen atom, but I'm a nitrogen atom connected to a carbon atom and another two carbon atoms and one hydrogen. Okay? So it inherits the properties of its neighbors. Okay? Similarly, the bond, let's say first pass it will just say I'm a single bond. Next pass it will say I'm a single bond between a carbon and a nitrogen, and so forth. Third pass it will say I'm a single bond between an sp2 carbon and an sp3 nitrogen or something like that. Okay? So in each pass you get more and more information from the neighbors and the neighbors' neighbors and so forth. Okay, and it's just stacking different layers like this, you're learning deeper relationships among in the data. Okay? So more network modules are stacked, you see longer distributions, longer range effects. Okay? So not just property of that functional group, but a property of that functional group in combination with another functional group, like say a pharmacophore, which means one group here with a certain distance, and another group here with a certain distance. That's all. And these pharmacophore models are often used in drug design to predict whether something will be active against a particular biochemical target or not. Okay. So some such thing is this magnet, which was a graph network like this, and it was trained on several guessing properties, and it was able to predict much better values for all of these properties. So this is the training set versus the test set, and this is the receiver operating characteristics curve. Using this, they were able to, within 17 days, to predict new materials for their new crystal structures, okay, which were targeted for a certain property. Okay, so and this is entire prediction process. We designed 41 new materials, all took place within 17 days, as compared to the 2 decades that it used to take earlier. Okay, and this is actually using active learning. That means not just prediction, but it's coupled with a robotic synthesis and testing device, so that you make a prediction, you have a training set, you develop a model based on that, predict new materials, take those materials straight into the lab, and maybe those materials are not yet, they are virtual molecules. Then synthesize, the robot synthesizes those molecules, tests them, and that tested data now forms your training data for the next model. So by this way you develop deeper and deeper models and are able to widen the domain of applicability of your model. So among these kind of deep generative methods, there are several classes which are used in chemistry: autoencoders, generative adversarial networks, graph neural networks, and transformers. Okay? Say a few things about each of these. Okay? So an autoencoder has a bottleneck architecture like this. So it has many neurons in the input layer, very few in the middle, and then a large number of neurons in the output layer. It consists of an encoder. This part is called the encoder, and this is the latent space, and this is the decoder. So what happens is that in forcing the model to encode all of this information in this small latent space, you are forcing it to learn a very compact representation of the similarity between the data. Okay, so it's able to map the different molecules on this latent space based on which molecule is similar to which molecule and so forth. Okay, so the goal is to minimize the info, and then the task is to predict that molecule back. So you study that molecule, and then you have to be able to reconstruct that molecule. Yes, if you are able to reconstruct the molecule perfectly, or almost perfectly, that means you have learned a very compact encoding of that molecular structure. Okay? So the input mapping to and from this lower dimensional space introduces a bottleneck which forces the autoencoder to learn informative features. Okay? Example here is you train these on smile strings, and you have this, you generate this is your latent space, and this red is your active molecule. So this is more active, red is active, blue is inactive, and you want to now focus on this region and say, I want to generate more molecules in this region. Okay, not just the molecules I was given. I want to generate more molecules in this region because that's where my active molecules are. That is a region of chemical space I'm interested in. So then you start generating new molecules, that's a generative chemistry, in that active region. Okay. And you can actually go from one molecule to another molecule by making small changes. This shows you the similarity. If you want to go from penicillin to ibuprofen, the red line shows you the similarity to penicillin, green line shows you the similarity to ibuprofen, and the similarity to penicillin is decreasing as you go, and the similarity to ibuprofen is increasing as you go. So you can guide how the molecule is going from the less active region to the more active region, for instance. Okay? And if you see, this is shows you how well it is the resulting molecules binding to the target receptor. Okay. In generative adversarial models, you have two neural networks. One is called a generator, and the other is called a discriminator. These two, generator and discriminator, they compete against each other in a machine learning game. Okay? So the generator tries to generate data that mimics the true data, whereas the discriminator tries to discriminate between the true and the fake data. Okay? So the generator learns to generate statistics of the data by trying to fool the discriminator. So trying to fool the discriminator into believing that the data, that the molecule that I made is actually coming from my training set. The discriminator is trying to tell apart the molecules which came from the training set with those fake molecules which are generated by the generator. Okay. And in this process, as the two compete against each other, like in any game, you slowly improve. Both the players improve. So both the generator and the discriminator improve in this process. Okay. And finally, you are able to get a much better model for this. So, and these are commonly used, generative adversarial models in chemistry are commonly used in combination with reinforcement learning. Reinforcement learning, as we said, learns by making errors, by trying things out, making errors. So rather than learning rules by brute force, it plays the game and tries and learns from its errors. This is how reinforcement learning beat the best human player in the game of Go. And this is similar to the number, now in Go, the number of possible moves is very, very large. This is similar to our chemical space. Chemical space, the number of possible modifications you can make is very large. Okay? So the algorithm avoids the use of brute force to examine the possible structures. So here, this is the reinforcement learning. You have an agent interacting with an environment, and the reward is based on the final performance, not the reward at each step of at each move. Okay. So if you're playing a game, you might be okay with sacrificing your pawn if in the end it leads to your king being saved. Right? So it's the cumulative reward that is important. Okay? So these generative models, they are there is different. We have seen some kind. We have seen the use of them to learn a certain distribution to generate molecules like the training set. We have also learned goal directed. That means not just to learn molecules like the training set, but to improve the molecules in the training set, the guided generation. And you can also have conditional generation, that is generate molecules like the training set, but with certain constraints. Okay? So I just want to talk about transformers before. Okay, so this is one common algorithm is called organic. It consists of a generator and a predictor, and they learn the SMILES representations. Their input, the SMILES representations. The generator generates new molecules. The predictor predicts the properties and discriminates between the real and the fake. The generator model is trying to provide molecular structures. Discriminator model rewards or penalizes the structures generated based on drug likeness. And the model learns directly the SMILES to relate the similarities between the molecules based on that SMILES strings, okay, without being given descriptors. So the discriminator determines whether a molecule is likely to come from the initial distribution or not. The reinforcement now, if it was just a generator, you just generate molecules like your initial distribution. But that's not what you want. You want to generate more potent molecules. So this was the original distribution of potency in your training set. And this is what you want to get. Okay, so this is output molecules generated is now this. So it's more active. Your the generated molecules are more active than the ones that were in the training set. And this is performed by the reinforcement learning. Reinforcement learning nudges the model in the direction of the given to increase the potency, to increase the desired property. So the generator tries to generate molecules that maximize the objective function, which is a linear combination of the discriminator and the reinforcement component. And this adversarial approach, that is the generator and the discriminator, tries to keep the generated molecules similar to the initial distribution of data, whereas the reinforcement learning biases the generator towards maximization of the desirable property, the potency or whatever. So this way you can see, for example, if you your initial molecules and your generated molecules, you see that generated molecules were had a higher melting point. So generated molecules were shifted in the direction of higher melting point. The model learns to extend the So, and here this is for organic photovoltaics. So you can see the average power conversion efficiency rapidly improves. And using this, they were actually able to generate new molecules, new drug-like molecules which are validated against mouse models within 46 days, compared to the 10 to 15 years it used to take for drug discovery earlier. Now within 46 days they are able to do this entire process. Finally, I want to mention a little bit about transformers. This is the famous transformer, Transformer 8. This is Ashish Vaswani. This is Nikki Parmar and other co-authors. And this was the paper which is attention is all you need. So self-attention, which is at the basis of your large language models, it was developed by Google Brain in 2017, and it is designed to process sequential data, remembering which previous token, that for instance we are feeding in smile string, which previous character in the smile string is most relevant for the smile, for a particular position. Okay. Then this provides a context for any position by examining the input string and deciding which parts of the string are important. To give you an example, for translating from English to French. English, you say the animal didn't cross the street because it was too tired, and this is how you would say it in French. So you can say the animal didn't cross the street because it was too wide, and this is how you say it in French. Then you see that the it is translated here into ill, and it is translated here into L, because in English the street does not have a gender, whereas in French it does. So here you use the male gender, and here you use the female gender. Okay? So at each point in here, translating the first sentence, the model learns that it has to pay attention to the animal. Okay? The it that is too tired is the animal. In the second case, the it that is too wide is not the animal, it is a street. Okay? So it tracks where it has to pay attention to. And when you do it with smile strings, this is the math for it. It's basically a set of matrix multiplications. And here you see how in each smile string where you have to pay attention to for a particular token. Okay. This is the architecture. There's an attention headers. Then like this you stack several different attention heads to create what you call a multi-head attention. Okay. An algorithm based on this for molecule generation is called M.GPT, and it was trained to predict the next token, the next character in the smile string, by feeding in a certain spice string. Okay, and you have a training and then a generation molecules. This is actually a small language model, unlike ChatGPT. GPT-1 has 110 million parameters. GPT-4 has 1.76 trillion characters, but more GPT has only 6 billion parameters. And masked self-attention is applied, and here the model was trained to constrain to within certain ranges of log T, synthetic accessibility, topological polar surface area, and how quantitative estimate of drag likeness, like Lipinski's rules, how many of Lipinski's rules you are violating and so forth. Okay? And if it's the vertical lines give it the target property, and the blue and green, the red and blue and green lines give you the generated characteristics of the generated molecules. This black curve gives you the initial, the training data. So you see the training data is broadly distributed, whereas the generated molecules are focused into that particular region where you wanted it to concentrate on. Okay. Similarly, you can just tell it not just to constrain it on one property. Like we said, we want to optimize multiple properties at the same time. So we can give it two different properties and tell it to generate molecules in this region, in this region, in this region. Or you can even tell it three different properties and you can tell it to generate molecules in a particular region of the chemical space. So it learns these relationships, and the generated molecules were more valid, they were unique, they are not just repeating the molecules in the training set, they are novel, and they are internally diverse. And they can be constrained based on certain properties if you want. Okay? And you can, just one example giving the language. So how is the language relevant to this, the drug discovery problem? Okay? Now these authors, they actually treated the binding of a ligand to a protein as a language translation problem. Okay? Now here, of course, the translation is not an equivalence, it's not that this word means this word, it's a relationship, that is this ligand binds to this ligand. Now you're translating from the spice language of the ligand to the amino acid language of the protein. Okay? So given that, they were able to generate new molecules which followed the distributions, the desired distributions that you wanted. Okay? And you can use this for polymers. This was done in this trans polymers to generate new polymers with specific properties. Let me skip that. And finally, just talk about the BERT, which is the deep bidirectional model. So the transformers generally read from left to right and they predict the next character. Okay. BERT reads in both directions and it's trained by just masking or blanking out some random characters in the spice string and telling it to predict those characters. So that's how. So here these characters are blanked out and the task is to predict this spice string intact. Okay. So after this training then, the molecule, so this is the pre-training stage, and then you in fine-tuning, you give it the property that you want to predict. Okay? So you pre-train it by doing this masked language model, by masking. In the pre-training stage, you're just reproducing the training molecules. After corruption, you're just reproducing the training molecules. In the fine-tuning stage, you give it the property you want to predict. Now it's learning the property that should be predicted. Okay? So that's it. I think that's this is how it performs, and as you can see, it performs better than other algorithms. Okay? And you can use it for DNA also. I won't go into that, but it's similar application. You can see that it's been used. And not only that, you can train this final side, and you they trained it on a human genome and asked it to predict the splice sequences in a mouse genome, in an entirely different genome in a non-coding region. Coding region, remember, has 85% orthologous region, whereas the non-coding regions of DNA have less than 50% similarity. And yet, by training on the human genome, it was able to predict the mouse genome. Now, what's the use? Why do I need to learn how to cure cancer in mice? We have very good models to learn how to predict cancer in mice. We want to learn how to predict cancer in humans, right? But if you can train on one smaller data set, a larger data set, and use it to predict the smaller data set, that's actually what you want. Okay? So with that, I'll just stop. And these are some of the things that
Thank you, sir, for the enlightening session. We got a clear idea about the data prediction with the help of various data set predictive methods.